That's the title. I'm going to talk about pyrochlores. So, but before I start, let me again thank the organizers for the invitation to be here. I was here once before and I really enjoyed it, so I'm sure this time is going to be the same. Um, so what I'm going to talk about is also talk is also split into two bits. The first part is going to be about some simulations we've been doing in pyrochlores, essentially preparing for an experiment, but we found that the results are interesting enough to be told before the experiment is done. And then the second part is going to be essentially the opposite of what Marcelo did, in the sense that it's an experiment that took us, the experiment itself, the measurement took something like a month. So Marcelo was talking about milliseconds, I'm going to be talking about a month-long experiment. As you can guess, it's an experiment on relaxation, which doesn't mean that we were very relaxed when we did it, but at least the sample was relaxed. Okay, so let me start by acknowledging the co-workers. So there's something against the iflisib, because here it should say iflisib and there should be more people there too. I'm surprised. Anyway, okay. So this was done in collaboration with Rodolfo Borsi, Victoria Ferreira, and Pamela Uruciaga, who are at iflisib, Daniel Cabra, who is here, and Flavia Barracin, who is here as well. And there it should say iflisib, and here it should say Gerardo Rossini at the Institute of Physics of La Plata. Then from the theory side, we also collaborated with Roderick Messner, Claudio Castelnuovo, Letizia Cuglandolo, and Marco Tarsia from Paris. And then from the experimental side, we worked with Alan Tennant, who is now at Oak Ridge, with Andrzej Sokolowski, and another who is at HZB, and another name that is missing there is Bastian Klemke, who took with Alan and Bastian and Andre with the relaxation experiment I'm going to talk about later. And the samples were both our own and from Prabhak's group in Oxford. So let me start with a very simple discussion about what frustration is. I know that many people here know better about frustration in the context of magnetism, and we all work, or many of us work in Latin America, so we know what frustration means at the workplace, but I'm talking about magnetic frustration. So there are different ways in which you can get magnetic frustration. One way, so let me start with the definition. The definition would be that you have a system with pairwise interaction and you're not able to satisfy all interactions at the same time. So how can that happen? One way which it happen is if you have disorder in your system. Let's say that you have a simple square lattice with Ising-like spins, and they want to be antiferromagnetic, except for one bond that wants to be antiferromagnetic. That's, if you want, the whimsical bond that wants to be ferromagnetic. And then what you find is that you cannot satisfy all these constraints, because if you satisfy ferromagnetism in this direction, then you're essentially messing up with one of the bonds. Another way is that if you have just, again, still in the square lattice, if you have further neighbor interactions, let's say you have all, in this case, they're all antiferromagnetic, but once you satisfy, let's say, the first nearest neighbors, then you see that the next nearest neighbors are not satisfied, so this is parallel with that, and you want them to be opposite. If you satisfy those, you see that you messed with the other two. So, from an experimental point of view, this one requires disorder, and we know that disorder is not very easy to control in the sample. Essentially, we try to avoid disorder, and when we add it, we try to add it in a controlled way, and it's very difficult. I mean, it's not impossible. There's a lot of nice work doing by doping samples and adding disorder in a controlled way, but or irradiating them, but it's not easy. So, let's say the first stage is better to avoid this kind of system. This one, you can see that it's really complicated to get, in the sense that theoretically it's very easy to say, the next nearest neighbor has exactly the same interaction that the nearest neighbors, but when you go to an experimental sample, to a real sample, it's very difficult to satisfy that both first and next nearest neighbors are exactly the same magnitude. So the third way, or one third way I'm showing here, is to base yourself on geometry. So here, this is the canonical example everyone gives when talking about frustration or geometrical frustration, is that what you have is, let's say if you have a triangle with all antiferromagnetic bonds, again, it's not possible to satisfy all of them at the same time. So the nice thing about this is that it's easier to control experimentally. So you can define, I mean, nature defines for you crystalline structures, and if you manage to grow them pure enough, and if the crystals do not distort, again, this is opposite to what Marcel was talking about, if they do not distort, then you'll have a frustrated system. Of course, we know that that's not completely true. So we can say that within certain ranges of approximations, these lattices would not distort, but if you nitpick, you're going to eventually find some sort of effect that is related with some distortion. It might be tiny, but you'll find it. I'm not going to talk about that this time. Okay, so what are the building blocks for this talk? I told you it's a pyrochlore lattice. Essentially, pyrochlore lattice is putting together tetrahedra. So, and in the case I'm going to talk about, these are Ising type pyrochlore lattices. So what we have is a tetrahedron, like here, and we have spins at the vertices of the tetrahedron, and they can point either in or out. So there are only two ways in which they can put, right? So spins in the vertices, and they're classical. Again, this is another approximation. They're classical spins pointing in or out. So the first question is, if I look at pairwise interaction, what's the ground state of that system? And this is way to see this, is by looking at a pair, right? So they can either point both out or both in, or one of them can be in and the other out, or conversely, one out and the other in. So now you see, if I choose a ferromagnetic interaction, these two, the ones that are both pointing in, have a bigger component of collinearity, being parallel than these four. So I'm going to pick these two states, and if I have an antiferromagnetic interaction, I'm going to pick these states. So what this means is that the ferromagnetic case has this rule that it's telling you that of the four, two have to be pointing in and two have to be pointing out, while the antiferromagnetic will be this boring case, if you want, between inverted commas, because I'm going to talk about, in the first part, I'm going to talk mostly about the boring stuff, where all of them have to point out, and all of them have to point in. So in the case of the frustrated case, where you cannot satisfy all the bonds, you said you have 6 possible combinations of 2 pointing in, 2 pointing out, while in the case of all out, all in, you have only 2 possible combinations. But this is for a single tetrahedron. So what happens when you put many of these together and you build a lattice? So what sort of ground states do you get? In the case of the frustrated ferromagnet, this is what has been called the spin ice. And the reason for the name ice is because essentially what you get is the same entropy of the ground state than what you get in water ice. So essentially what happens is that when you put all these together, now you have a further constraint, which is, of course, when you put 2 tetrahedra together, the spin has to be the same at that vertex. So essentially what your ground state entropy will be is you have 1/2, so you have of the 4, once you start putting them together, you have 2 spins per tetrahedra. And of those, you have 6 possible choices. I told you that for a single tetrahedron, you can have 6 choices. But there's only 1/4 of a chance to match that this spin is pointing in the same direction, that it's the same spin in the next tetrahedron. So that gives you these 3/2. And for any of you who have looked at the water ice literature, you'll recognize these as Pauling's entropy. And essentially, in this extremely simple model, we're not taking into account more than nearest neighbors. You see that the entropy you get is the same that the entropy you get for hydrogen in water. So essentially, the states of pointing in, pointing out are equivalent to being covalently bonded or hydrogen bond, like in water. Okay, so this was the interesting spin-ice state. And then the boring state, as I said, only has two possible ways. Once I choose one of the tetrahedra to have all of them pointing in, those will be the blue ones here. Then the next tetrahedron has to have all of them pointing out. Those are the red. And once I decide one tetrahedron, all the rest fall in the same direction. So the residual entropy for that state is 0. Okay, for spin-ice, we already know, this is a work by Bramwell and collaborators in 1999 or 1997, where they found at least two materials that are nice spin-ices within a very good range of temperatures. So essentially what you have there is a pyrochlore lattice. This is a simplification, of course. What if you look at the crystalline structure of dysprosium titanate, you'll find that these are two intertwined pyrochlore lattices, but only one of them, and the oxygens are all around, but only one of them has magnetic moments, and those are one pyrochlore lattice, and those magnetic moments are Ising spins. This is because of the crystal fields. They are Ising spins to within 300 K, and we're going to be working below 1 K, because the ferromagnetic interactions are of the order of 1 K. So to within all extent and purposes, we can think that these are nice Ising spins, but they have a very large magnetic moment. So this idea of just looking at nearest neighbor interactions certainly does not work. You need to take into account that there's dipolar interactions as well. And the nice thing about these two materials is that they're very easy to grow. I mean, you can give a summer student the project of growing one of these, and it works. So you can get really large, nice single crystals of either dysprosium titanate or holmium titanate. So for the experiments I'm going to talk about, for the neutron experiments I'm going to talk about, and for the heat experiments, we used isotopic sample. The reason why we choose this isotope is not because of the cost, because the cost of this is something like 10,000 times the cost of a non-isotopic dysprosium, but because these have no nuclear moments. So we wanted to have the cleanest possible sample, in the sense that we only wanted the spins, the contribution from spins, not spins from the nuclei. But the other reason is that dysprosium in natural abundance absorbs neutrons quite a lot. So if you want to do low temperature neutron experiments, you need to use some sort of isotope, otherwise they would heat up quite quickly. So one way in which people showed that this hand-waving way of counting entropy worked reasonably well for the system was by doing exactly the same thing that people had done for water ice, which is measuring the specific heat, integrating the specific heat, and seeing whether that matches with your expectations or not. So this is a work by Ramirez and collaborators in 1999. And you see, this is what you get for the specific heat. Let's first focus on the zero field. There you have this peak close to 1 Kelvin. This is not a transition. This is just a simple Schottky-like peak, which is telling you that there's some energy scale there, but there are no sharp features. Then when you integrate that out, you start from 0, you integrate it, and you see that you reach something which is not the limit you expected. So the limit, the high temperature limit, should be that these are simple paramagnets. So you expect this to be R log 2, but you see that you reach somewhere below, and the difference between where you got and where you should have been is of the order of your residual entropy, which matches reasonably well with Pauling's estimate. Where, again, Pauling's estimate is something, it's an approximation on top of an approximation, but it has been shown that it works very, very well. So there's no exact solution for the entropy of a three-dimensional ice system, but it has been shown that within more than a part of 1,000 Pauling estimate is good enough. So essentially what you're missing when you're doing Pauling is I talked about one tetrahedron and the neighbors, but I didn't talk about any correlations. So what happens is that it's easier to find a matching spin than just purely random. You see that you have these positive correlations that very slightly increase the entropy. But anyway, that's not what I want to talk about today. So what I want to talk about now, it's this idea of this emergent gauge structure. This is an idea that started with Roderick in 2007. The idea, I think it's very beautiful, in the sense that what he's saying there is something like this. Okay, so I told you that the way in which you constructed this ground state is like saying that 2 of these spins pointed in and 2 of these spins pointing out. So essentially what that translates is that saying that the sum of these spins on a single tetrahedron is 0. So if you now go from the discrete to the continuum, you can say that this is equivalent to saying that the divergence of some field is 0 at the ground state. So then you can say that you have some sort of a field there, so the curl of some vector field that corresponds to some charge. So essentially you're saying my ground states correspond to a new, and every time I have an excitation, I can associate that excitation with charge. So the nice thing about that is that once you do that, you have a description for a ground state and a description for excitations that essentially doesn't need the spins. So you can work with that and you can forget about the spins, which are quite complicated. Again, to a certain degree of approximation, I'm going to discuss that. Okay, so what I'm saying translates to this. You have, this will be your 6 states for the tetrahedron at the ground state. Those are your neutral. Once I flip a spin, I see that the sum of the spins here is positive, and I can have either charge of 2 or charge of 4, or I can have charge of -2 and charge of -4. Right? So I have 4 possible excitations, so 8 possible excitations, and 2 excitations to even a higher level. So I mentioned from the beginning that in the materials we have, dipolar interactions are important. So to which extent that this nice picture survive dipolar interactions, and you think of spins as dipoles, and everyone, you know that if a student says something like this in a undergraduate exam, the student immediately fails the exam because spins are not dipoles. But if you're looking them from very far away, you can think of spins as dipoles. And then you see that this idea translates pretty easily in the sense that what you're saying is that if I have 2 spins pointing in and 2 spins pointing out, the charge inside one of these tetrahedron, one of these tetrahedra is going to be neutral. So it's going to be 0. So this already gives you 2 things. It gives you one easy way of seeing that even in the case of dipolar interactions, the picture survives, and it also gives you the extent to which it survives. So if any of the phenomena you're looking at is within a length scale that means that spins can be thought as dipoles, then it's fine, you can use this picture. But if you focus to a single or a few tetrahedra, then it's not going to work. So everything I'm going to talk about, it's in macroscopic samples, so this picture is good to use, and it makes things quite simple for us. Okay, so the other thing that adds this dipolar interaction is that now these excitations are no longer free to move. So if you need to do a calculation, I'm not showing it, but it has been done by Casanova, Messer, and Sondi in this Nature paper. You can do the calculation, and you see that these charges interact with each other with a simple, if you want, magnetic Coulomb law. So the force between them goes like 1 over r squared. And these charges you can calculate. So the first way in which you can check whether this picture is good for the experiment or if it's complete nonsense is by doing this. You say, okay, if I have my sample and it's at a low temperature, what I expect is that I would have my excitations would be pairs of these charges. And now I can essentially, this is one of the beautiful things about this picture, I can take all the results I knew from electromagnetism and use them for this sample. So I can use the bihucal theory and calculate what will be the specific heat I expect for some density of charges, and this is what you get. So this is the measurement we did. This is heat capacity as a function of temperature. What's relevant is below 1 K, which is, so as I said, you need to be at low temperatures, because otherwise if you have many of these excitations, it's no longer true that you're looking at a long length scale picture. So here the two calculations are, this is a better lattice calculation, where what you're doing is you're neglecting, so you're constructing a lattice that looks a lot like your sample, but you cut all connections other than first nearest neighbor, right? So you put one tetrahedron, you put all the neighbors to that tetrahedron, and then you keep putting neighbors to those tetrahedron, but you never connect the neighbors with each other. So it's a good approximation. It's a very good approximation at high temperatures, but you see it fails at low temperature because you're neglecting correlations. And this blue line here is using the bihucal theory, where essentially you have no adjustable parameter, in the sense that the charges, because these are dipoles, you can calculate what would be the equivalent charges, and the only thing that changes with temperature is the density of these monopoles, which should go like Maxwell distribution, so there's not a lot you can use there to mess with. And you see that at low temperatures it works pretty well, so within this range of temperatures it works pretty well. But of course, once you're at high temperatures, it no longer works. Right, so this gave us the confirmation that it was this picture of charges was good to work with the spin ice system. So I'm going now to go back to the antiferromagnetic case, the boring case, and ask whether this picture is any useful for that case. Right, so this is just some random spin contribution, and now I can always translate some spin contribution into charges. And these are charges that move on the dual lattice to the pyrochlore. So these are charges on the diamond lattice, right? So because they move from the center to center of the tetrahedra. And the nice thing about that diamond lattice is that this is a bipartite lattice. The pyrochlore is not bipartite, but the diamond lattice is bipartite. So that's another thing that is going to help us to work with an antiferromagnet. Okay, so once we convert that, we said, okay, so is there anything interesting that can come out of this? Okay, what happens if you put a magnetic field to the system? And now we're putting a magnetic field along the 1,1,0 direction. And let me look at this pyrochlore lattice from the top. See that if I look from the top, I have two kinds of spin chains. These alpha spin chains, these yellow chains, and the beta spin chains. And I'm putting the field so that the field is parallel to the alpha chains. So the field is going to polarize the alpha chains, and it's going to do nothing with the beta chains. So what happens with the ground state then? So you know that, as I said, in the antiferromagnetic case, they're all pointing out, all pointing in. That means that I have double charges at each side. And now I start putting a field, and I'm going to change these spins, the spins on the alpha chains. And so what's going to happen is that I'm going to polarize these spins on the alpha chains. And essentially, once I polarize those, you see that I need to have one pointing in, one pointing out. So the field is going to kill the double charges. I'm going to get single charges. And because the field does nothing to the beta chains, this is a perfectly disordered single state charge. So this is the zero field case. This would be the double charges, the single charges, and the neutral. This was the ground state, as I told you. I had to excite the system if I wanted to get single charges, and I had to excite it even more if I wanted to go to the neutral case. This will be the ferromagnetic case. Right, so what happens as a function of field? Well, you see that the field does nothing to the energy of the double charges, because these are this is a perfectly zero magnetic field, zero magnetization state. So the magnetic field does nothing to that, but it lowers the energy of the single charges and of the neutral charges. And what we found was interesting was to work within this square, so within this range of fields, where now your ground state is of single charges and your excitations are double charges. So you have like your ground state is like this liquid of monopoles, and your excitations would be to make them double charges. So what's the entropy of the system? It's not there. I mean, it's no longer 2. So the number of states is no longer 2, but it's also not really exponentially degenerate. It's only sub-extensive. You see that if you now look at the entropy, this is for Monte Carlo simulation. So if you look at the entropy as a function of temperature for different system sizes, you see that although at L equal 2 you don't reach even at 70K you don't reach R log 2. As you start increasing the system size, the entropy scales like you can show that the entropy scales like L squared. So it's not giving you an extensive entropy, just a sub-extensive entropy. And the reason for that is because, as I said, this entropy is coming from the beta change. So all the alpha change are polarized, and you only have something that goes like L squared. So it's not. It's marginally. It's marginally degenerate. I mean, it's not like the spin ice case. Okay, so what happens if you look at this specific heat? And here, again, I'm showing the results coming from Monte Carlo simulations for 2 different lattice sizes. And this will be the symmetry calculation. This is, it's neglecting correlations, but it's the infinite lattice limit. And these are 2 more models you can do where you project these spins into 2-dimensional systems and you can estimate the specific heat. But essentially, they all coincide, if you want, in showing that there's some feature in the specific heat at low temperatures and another feature at higher temperatures. So the way in which you can understand these features is by looking now at the, not simply at the charge density, but at the staggered charge density. So what I'm calculating is the density. This is like if you want, in an antiferromagnet. So the staggered charge density means that you remember that I said that this diamond lattice is bipartite. So I can define the 2 sublattices. Now I'm going to calculate what's the density in one sublattice and the density in the other. And rho S is going to be non-zero if I have opposite charges in the 2 sublattices, right? So I can calculate this for single charges and for double charges. And this is what you get. So this is the staggered density for single charges and the staggered density for double charges. And you see that what's happening, let me start with the single charges. Again, the color code is the same. This line corresponds to the infinite symmetry limit, and this is for 2 lattice sizes. So this is for 128 spins, or for 1,024 spins. You see that this feature moves to lower temperatures as you increase the system size, and when you're in the infinite size, it's just a very sharp step. So at 0, you have this density 0, but as soon as you put a little temperature into the system jumps into a state where this density, staggered density, is non-zero, and it eventually goes to 0 when you have the second transition. So there's this temperature range where the system has single charges and also has some density of double charges. You see here that it jumps to 1. As soon as you put small fill, it jumps to 1. So what's happening here? It's something that it's familiar to many of you, I'm sure. It's this phenomenon of order by disorder. Let me first say a couple of words, a very simplistic description of what's order by disorder, and then I'll show why it works in our system. So the idea is this. You have a set of ground states, and now at 0 temperature, the system is certainly going to be in one of these ground states. But then if you're looking at the system at a finite temperature, a non-zero temperature, you need to ask not only what are the ground states, but what is the density of excitations around those states. If you have something like this, so this will be in phase space, this curve will be all your ground states, and the black curve will be that, and the green curve are the excitations. So if these excitations are more or less uniformly distributed, nothing particular would happen. Oops. But if you now have a possible case, where there's one particular region close to your ground state that has a higher number of excitations, then as soon as you put a temperature, entropy is going to favor, so in the free energy, the entropic term is going to favor being here. So essentially what happens is that because of entropy, because you have a lot more excitations available when you're close to this point, you spend most of your time there, and essentially what you'll be doing is by ordering your sample by putting temperature. This is the idea of order by disorder. So you order between where the sample by increasing the entropy. So how does that work in our case? So as I told you, what the ground state is when you put this field, it's just this disorder soup of single charges. But now, let's say you want to flip one of these spins in that case. So I'm comparing the case where the system is completely disordered when the system is ordered in this way I told you, right? So for this state, you see that one blue charge has all red charges around. So this is the case that will give you a rho staggered equal 1. Let's say I flip that spin. So in one case, what I'm doing is I'm creating a double charge here and a neutral side here. While in the other case, what I'm doing is I'm creating two double charges. And as you remember, the excitations closest to the single charge were the double charges. The neutral side cost you a lot. So these type of excitations would not be allowed at low temperatures, but this type of excitations would be allowed. So you see that if you start from an ordered system, it's a lot easier to get excitations than if you start from a disordered system. So as soon as you put a little amount of temperature, the system tends to order in charge. So you get this charge ordering. Now, that explains the first transition, and the second transition is a simple disorder by disorder transition, where essentially what's happening, this is just showing the susceptibility and how the susceptibility scales. It's just a normal Ising type transition. What's happening is at higher temperatures, now, so you can see it from here, this will be the density of, in the system of single charges, double charges, and just the neutral case. So when the neutral, because of thermal excitation, because the number of neutral sites you have is comparable with the number of double sites you have, this mechanism is no longer at work and the system simply disorders completely. Okay, so there's one more thing you can do. If you're not convinced that this is an order by disorder case, you can, because we're doing simulations, you can do this easier. So you can calculate the density of states for your system and see whether this picture here is true. So we did this Wang-Landau algorithm to calculate the density of states, and we're plotting here the density of states of the system as a function of the energy, as a function of this rho staggered parameter, right? So this parameter here will be the parameter that parameterizes this curve. And you see that when you are at rho equal 1, you have this big peak in the density of states at a temperature which is of the order of 0.1. Right, so what this is telling you, this peak will be the equivalent of that blob there. And what's telling you is that when you are at this rho staggered, you have all these states that are available that are not available if you're at any of these other points. You can say, okay, how can I mean, this is a peak. Is this statistically significant, or is it just a peak? Okay, so you can check whether it's statistically significant, but just saying, okay, I'm going to calculate my rho. If I know the density of states, I can always use the partition function and calculate any observable. In particular, I can calculate what I expect to see for rho and compare that with what I see from the simulations. And you see that this is the light blue is the simulations, and the black crosses is what you get if you use the density of states and you calculate the rho. And you see that at low temperature they are one on top of the other, and these dots here are additional ways of calculating by chopping slightly your density of states and seeing whether, if you keep that peak is still statistically significant. And you see that it's essentially a pretty consistent picture. Okay, so that's what we did in preparing to the experiment, and that's the stage we're at now. I mean, we are pretty confident that if we find a system which is an antiferromagnetic pyrochlore with Ising spins, we should be able to measure order by disorder. And these are our candidates. As I said, this is still work in progress. We know that these there are at least these two candidates that are supposed to be antiferromagnetic Ising pyrochlores. The problem is that because this is a very low temperature phenomenon, you need to have very clean antiferromagnetic pyrochlores. If you have additional interactions, those interactions tend to mess with this picture and you don't see anything. So we're characterizing these samples now and seeing whether you get no order in the simple zero field state. If you get perfect antiferromagnetic order in a simple zero field state. Then you can also think about constructing this by using square lattice spin ice, right? By etching this onto some system. There are some groups working on this, and we're talking to them about doing it. And you can also think of a colloidal system. This is a proposal for someone else. I mean, we're not going to try doing these optical traps. The other thing we checked is that even in the case where you have dipolar interactions, and even in the case where slightly misaligned, because you know that in Monte Carlo it's very easy to say the field is pointing in this direction, when in real life it's a lot harder to do that. And we checked that within 5 degrees of misalignment, this picture should still be valid. Okay, so that was the first part of the talk. And now I'm going to go back to the ferromagnetic case and ask about the effects that go beyond this nice monopole picture. So, as I said, there's the dipolar term, and to a certain extent, we could forget about this dipolar term. But when you are at sufficiently low temperatures, you cannot neglect the higher order terms in your dipolar interaction. And what happens is that this dipolar interaction should, in principle, order the system at very low temperatures. So in theory, there's no real spin-ice material if they have dipolar interactions. So this is a work done by Melko and collaborators. This is in the work of Michel Changrat in Waterloo. So as early as 2001, they predicted that once you take into account that these have these really large magnetic moments, so you have a dipolar interaction, the system should order, if you use the parameters for dysprosium titanate, you should see this black curve here is the simulation compared with one due experiment by Ramirez. You get this smooth Schottky type anomaly, but then you should get a very sharp transition into an order state. So this is a prediction of how that order would look. Essentially, it's still a neutral charge state, but of all the possibilities you have, you're restricted to 6. Essentially, what happens is that you get this change that order. So you see all these spins pointing in that direction. So you get like an antiferromagnetic ordering of these chains. And essentially, you see that it looked like Ramirez had stopped a bit too early. He should have gone a little further down in temperature, which is, of course, very easy to say later. But even if you can see that there's already a discrepancy there between the theoretical prediction and the experimental measurement, it was attributed to the fact that, okay, well, the parameters are not completely perfectly determined, so maybe what's happening is that this is slightly at a lower temperature, but it should be there. So according to the simulation, if this is the true Hamiltonian, it should be there. So what some people did was to take a whole bunch of experimental results and try to fit all those results with, not just with the dipolar and nearest neighbors, but to add dipolar, second nearest neighbor, and third nearest neighbor. And they saw that even in that case, you should get essentially the same kind of order. There's some work we did together with Gerardo, Daniel, and Flavia, and Diego Rosales, who is not here, where we also tried to go a bit further by looking not only at the field experiment, but at higher field experiments. And we saw that not only third nearest neighbors were important, but you had two kinds of third nearest neighbors, and it was important that those two were slightly different to explain the results. And we think that that is probably coming from small lattice distortion. So as I said, even in a system that you think is perfectly frustrated, there are always, if you refine your analysis enough, you'll find that there's some evidence of something that's not perfectly what you think it is. Okay, so going back to this, why wasn't any kind of peak seen there? So one explanation was that there's this really huge increase in the characteristic relaxation time of the system. See, this is temperature, and you see that here the system goes, this is in seconds, the system goes from 10 to the minus 4. When you're close to 1K, the system has already relaxation time of the order of 1 second. And if you check this slope, it's going to be really, really steep. So in principle, you should wait for a really long time to measure, to be able to see any equilibrium phenomena in this system. So that's what these people did. This is work by Pomaransky and collaborators. This is the work of Kichia, also in Waterloo. This is an experimental work. So what they did was to say, okay, if we need to wait, we'll wait. And they measure specific heat. And you see here, this is the time of the relaxation measured in seconds. But you see that essentially for some of these curves, you have to wait for 2 weeks. So now when they compared their results with results by other people, so for example, this is Ramirez, the one shown here is Ramirez. This one here is Klemke, so this is the measurements we did. And this is the measurements I showed you at the beginning that that intermediate range of temperatures work well with the monopolar picture. But when they waited for long enough, they saw that there was this upturn that seemed to indicate that they were seeing that if you waited long enough, you could see order. Okay, so if that was what's happening here, then you say, if I do the same experiment with neutrons, I should be able to see the order that is developing there. And the only thing you need to do is to wait. Of course, as many of you would know, it's not easy to wait when you're doing neutrons because everyone wants to do an experiment. And you only get very small allotments of time to the experiments. So what we did was to say, okay, while we wait, we don't need neutrons. So we went to Berlin and we waited till there was some shutdown of the reactor for maintenance. And we put our experiments while they were maintaining the reactor. We waited, and then we did the experiment. And we did this twice. So we waited for 2 cycles of maintenance, and we prepared our experiment. This is what we did, right? So this is the temperature for the 2 cycles. We did the temperature as a function of days. And you see, we did a very slow relaxation. We waited for, the first time we waited for around 10 days. And then here, we did the experiment, we started measuring, we started ramping up the temperature, and then we did a quench to see whether there was any difference between waiting for so long and just quenching the system. We did this once, and the second time we started even earlier. We waited for about a month measuring the temperature and waiting for the system to relax. And then we did a set of experiments, something very similar, right? So we ramped up the temperature. So if you compare this with what you expect, this would be the characteristic time obtained different ways, particularly by looking at, this is the work by Snyder in Penn State, by looking at frequency-dependent susceptibility, you can estimate the characteristic time. Those are, that Arrhenius law is coming from those experiments. This is the specific heat experiment, the one I showed you by Kichia and collaborators. You see that they were well in equilibrium here, and they were slightly below equilibrium at about 0.4. And these are our 2 runs. So the first run, you can say that we were well at equilibrium down to about 0.4, something very similar, slightly lower than the specific heat. And for the other that we waited even longer, you see that we went to something like 320 milli-K. We were still in equilibrium. As you see, because this is something that exponential, there's no point in, if you want to go slightly lower than this, you will need to wait an exponentially larger amount of time. So this is where the experiment ends. I mean, we're not going to wait for 2 years with the system in place to see where we can go further down. Okay, what's the surprising thing here? The surprising thing is that we found absolutely nothing. So this is our experiment so this is the S of Q for just one cut of this S of Q for 300 milli-K after waiting for a month. And this is what you get for 300 milli-K after waiting for nothing. So if you do a quench and you do the neutrons, you see this, and you see that there are no black peaks here, indicating order. But if you waited long enough, there were no black peaks there. The temperature is here. So even if the system were not completely ordered, you see that the specific experiments were claiming that they were already seeing this evidence of some kind of order developing. We find absolutely no order at all developing at low temperatures. If you say, okay, it's very difficult to compare two pictures, now what I'm showing you here is just the raw data, the pure raw data, right? This is for two cooldowns. One, the very slow cooldown, and the quenched cooldown. And it's raw in the sense that you can even see here, this ring here is the aluminum lines coming from the can where our sample was. Now you subtract these two, and you see that there's absolutely no difference between 1%. There's no difference between what you see when you quench, when you wait for very long, and when you don't wait. So this is an open question. Why is it that there was something seen in specific heat and we see nothing? But the other question is, why is it that even when we know that there are dipolar interactions, the system is certainly not ordering at 300 milli-K? There's no hint of order at 300 milli-K. So that's, I wanted to talk about two ongoing experiments. One is an ongoing work, which is eventually going to become an experiment. And this is an ongoing experiment, and we don't have yet any definite conclusions of what's happening here. We have proposals of what might be happening. We think that this picture I told you about, where distortions come into play, might be a simple way of explaining what's happening here, because distortions, essentially what they do is they change the J3 and J3 prime, and what that gives you is that you get different possible orders depending on what's the difference between J3 and J3 prime. So if you have a sample that has some tensions in it, and it's very difficult to have a massive sample that you can use for neutrons where you have tension, where you don't have tensions. If you have some tensions, what you're going to have is this competition between different parts of the sample wanting to be at different ground states. That might be one simple explanation why when you do these neutron experiments, you see something something disordered. So what we're doing now is we're working at slightly higher temperatures. We're doing very careful neutron experiments measuring the S of Q. And we're using, this is being done at Oak Ridge, we're using these advanced fitting techniques to try to extract some Hamiltonian out of all these S of Q. So it's amazing the amount of data you can get now out of a neutron experiment. So in a few weeks, you can get a few terabytes of data that you can then use to fit and extract a very accurate Hamiltonian, if you want, very accurate empirical Hamiltonian. So that's what we're doing now, and we're trying to now calculate what sort of pictures you can get where from that very accurate Hamiltonian you can still get a disordered case. So that, as I said, this is work in progress. So to sum up, I told you about two pieces of work in progress. The first is this idea that even in the antiferromagnetic pyrochlore, which in principle is the boring one where the system orders at low temperature, by adding a magnetic field, you can get some interesting effects, like this perfectly classical example of order by disorder, classical in the sense of non-quantum. I'm not saying that this is a classical experiment, I'm saying just it's non-quantum experiment. And then in the ferromagnetic case, we're seeing that these subtle bits of the Hamiltonian and these subtle interactions, or if you want, these subtle distortions, are important in determining what's the ground state when you have a very frustrated system, right? So usually what happens is that interactions are so important that you don't need to worry about the minutiae of the interactions. But here, because all the main interactions are conflicting with each other, you leave room for these tiny interactions which are always neglected to say, okay, I have something to say, and this is I'm determining what's happening with your ground state. Okay, so with that, I'll thank you for your attention.